Sure. Yay. All right. You guys can see that okay, right? Yeah, you can see it? Okay. So today the plan is to discuss scattering. Yay. Scattering in quantum mechanics. And so last time I tried to motivate it, or motivate's the wrong word, but I tried to connect the concept of scattering to something that you've already thought about a lot, which is it's one-dimensional reflection or reflection transmission problems. This is something that you thought a lot about in your previous quantum mechanics course. And so I want to connect scattering to something that you already know, so you can start thinking about it. I find that helpful personally. And so I already did this, but I just will remind you what we were talking about. In order to introduce scattering, we can think of some barrier problem. Let's think of a one-dimensional barrier, and you know that if you can think of sending a particle at it, gives me an amplitude of e to the I kx, but then there's an amplitude to be reflected, which is r e to the minus I kx, and the wave function on this side of the barrier, I'll call it the left side, is the sum of those two amplitudes, because there's an amplitude. And when I say amplitude in your mind, you should be thinking probability. There's like an amplitude to go forward and at the same time an amplitude to be reflected. So we got to add those two amplitudes together in quantum mechanics. And then there's an amplitude to get through, Te to the I kx. And so that's the wave function on the right-hand side of the barrier. And so then you guys know that the whole point, what you did last semester was you had to find the T and the R. And that's basically the scattering problem, is to find the T and the R. So you did it already, and you did it by solving the Schrodinger equation and matching boundary conditions and all that. I won't get into it, but that was the whole point. But now, that's what you did last time, but now I want you to think about it in a new way. The new way of thinking about it is to think about it in terms of probability flux. And probability flux is not a new concept. You learned it last semester, but you probably just promptly forgot about it, because it's just, in first semester quantum mechanics, probability flux is just like a cute little nuance, just a little weird little thing you learn, and then it's not really good for anything, at least in my opinion. But in scattering theory, it's really important. It's a central concept, and it's actually, the concept of probability flux is much more important than you might ever suspect. For example, if you want to understand electrical current flowing through small devices, you have to use probability flux. That's the modern theory of electrical conductivity in condensed matter physics. Is all based on probability flux. So it's a very central concept that you need to engineer computers of the future. People will be basing them on probability flux. So it's really, it's not just academic. Okay, so here's probability flux. It's this little formula that you all learned. You were hoping you would never have to use it again, because it's so weird looking. Psi star ddx psi minus psi ddx psi star. How could that possibly be useful? And yet it is. So this gives you probability flux, which in one dimension is probability per time. In 3 dimensions, it's probability per time per area. But that's just a dimensional thing. We don't need to get into that. And so if we now, so the new way of thinking is that if we want to think about so now the new way of thinking is that the probability to reflect from the barrier is equal to the probability flux of the incident wave minus the probability flux that you get with the barrier. And so that's the probability flux that you calculate by using that wave function on the left side, this guy, I'm circling it. And then you normalize, you divide it by the probability flux that you would, of the incident, what you sort of start with. And so that's, and so now we're thinking of probability in terms of like water. We spray the hose, we have the incident amount of water that goes, but some of the water bounces and sprays back into our face. See, that's how I want you to think about it. And so if you actually calculate these quantities using this formula, and I'm skipping that part, I want you to do it on your own, you're gonna get this, R squared. And similarly, and so in the new language, we can call this the cross section. And I know that you've all heard of that word before, cross section, but most of you probably don't really know what it even means, but you know it has something to do with scattering, like the probability to scatter is cross section. And so this really, in some sense, is the cross section of this process. And so then you can find the probability to have transmission, and then using the same language, we can say that it's the probability flux on the right-hand side of the barrier. That's like how much got through, divided by how much was incident. And then if you calculate that, you'll see that that's t squared. And then, of course, we have conservation of probability, which tells us that the stuff that gets through plus the stuff that gets reflected is conserved. It has to equal 1. There's only a finite amount of probability. Okay, so that's sort of recasting an old problem in new language. And so now let's get more into the theory of scattering. But to talk about scattering, we have to start with the classical theory of scattering. And to be honest, I think that the classical theory of scattering is more difficult than the quantum mechanical theory, in my opinion. I think the classical theory is even more weird and hard to understand. Sometimes quantum mechanics is easier. But let's talk about the classical theory of scattering. So here's scattering. So here's some axis, and let's put a scatterer here. So that could be anything. That could be an atom. It could be a proton. It could be an electron. It's just something. And that thing has a potential. All right, so that's some potential, who knows what it is. It could be a quark, who knows. And so then what I do is I shoot something at it. And here's the thing I shoot. And so I shoot something at it, and that thing has energy E. And so I think of this as sort of like the kinetic energy that I start with. Because from far away, I can shoot something and know the kinetic energy of the thing I'm shooting. I know the energy. I can shoot a BB, bing, from a gun with a known velocity, momentum, and so I know the energy of that thing. And so it comes at my scatterer, and let's assume that this scatterer is fixed for simplicity, just to make things easier. It doesn't have to be fixed, but that makes it easier. So I shoot this BB at it, and there's a vertical distance here. This distance, there's this vertical distance here. We'll call that B. Does anybody know what that vertical distance is called in classical theory of scattering? It has a name.
It's called the impact parameter.
Yeah, how do you know that? Where did you learn that?
I microlensing research in astrophysics.
Oh, okay.
We do the same, like how offset the lens and the source are is impact parameter too.
That's good. Yeah, it comes up all over the place. Okay, that's the impact parameter, exactly. And so you shoot the little BB, but then what happens is that as the BB gets close to this scatterer, it starts to deviate. And if it's repulsive, it will start to bend away. And so it will shoot off into the distance asymptotically. Let's see if I can draw this good. I'm having trouble drawing these things. But it shoots off into the distance, lives happily ever after, and it goes off at some angle that I can define, theta. And theta also has a special name. Theta is the scattering angle. Scattering angle. And so that basically defines the classical theory of scattering. That's it. You have E, you have B, you have V of R, and you have theta. And so the classical theory of scattering is just to basically figure out the relationships between all those quantities classically using F equals ma. So that's scattering. That's scattering in a nutshell. That's classical scattering. And so, for example, in the classical theory of scattering, what you would do is you would say, if I gave you E, B, V of R, then what is theta? So that is the classical theory of scattering, is to calculate theta from all those given things. And so, if this was a classical mechanics class, that's what we would do. But we're not going to do it because classical mechanics is all wrong anyway, so who cares about it? We're going to do the quantum mechanical theory, which is more correct. But let's keep thinking about it. And so if you want to understand this, let's still think about it classically. It's useful. Those classical concepts are useful to set up the problem. And so what we do is you think about it like this. You want to, there's a connection between this impact parameter and theta. And it's useful to think about that, because the way it's very important to think that if I have some potential here, then if I shoot a particle at it, the particle's coming in and it just gets deflected off into the distance. But here's the thing, this particle, usually you're not just shooting one particle, usually you're shooting a bunch of particles. And so think of it like this. There's an L equals the luminosity. Luminosity, that's just equal to the number of particles per time per area, which is just equal to particle flux, okay? So in most experiments, there's really a flux of particles. So let's not just think of just one, let's think of a whole flux. It's easier that way. The statistical probability way of thinking is easier if you think of many particles. And so instead of just having one particle, I'm shooting a whole zillions of them, flooding like a whole stream of particles at this potential. And so that means that instead of just one particle, I can think of a whole bunch, and I can think of them as all going through this donut annulus. And so this is this famous construction where I have this little bit of area, this annulus, and the annulus has a radius is equal to the impact parameter. And so you can see that all the particles that go through that annulus, and that annulus is perpendicular to the direction, it's flat, it's like a donut, then all the particles that go through that annulus are deflected into that same angle, theta. Because you see even the one down here is deflected into the same angle. Because what we say that there's azimuthal symmetry. Or I should say, let's call it cylindrical symmetry, cylindrical. Because you can see how it has this cylindrical symmetry. And so what I want you to understand is sort of this, so then, okay, so let's keep going. So now we want to understand this geometry that I just drew. And so it's useful to think about it in spherical coordinates. So in spherical coordinates, we'll draw a big sphere. That's what spherical coordinates is all about, spheres. So this and the spherical symmetry really is coming from the potential. So let's assume that V of R has spherical symmetry, and that's usually the case. So the spherical symmetry is coming from the potential, which has spherical symmetry. It depends on radius, not angle. Okay, and so we draw that sphere, and then we notice that these particles that are deflecting, they are deflecting out of this. What I do is I follow all the particles that go into this annulus, and I notice that they all come out of, there's a solid angle. So I can define a solid angle like this. Construction is starting to get a little messy, but I want you to see it. It's like an eye, like the iris of an eye. I like to think of it as like a big eyeball, and so that helps. And so, because it looks like an eye, doesn't it? And so this is a solid angle. And so I'll call it d omega. That's a solid angle, that shaded part I just drew. Whereas this here is, what is the unit of this? This annulus, what is the unit of that? That is, what I've shaded here is a solid angle, but what have I shaded here? What is the units of that? Can someone tell me?
I guess it's like a little differential area.
Yes, exactly. And so we call it d sigma, where this is a little tiny area, and this is a little tiny solid angle. It's a piece of solid angle, and that's a piece of area. And the point, and this is a very important point, is that there's a relationship, a very important relationship, That important relationship is between d sigma and d omega. They are not independent, they're connected. What connects them? Can you, like, what is connecting d sigma and d omega? Why are they not just random, independent variables? What's connecting them? Somebody tell me. Think, look at the picture. What is the connection between d sigma and d omega? Why would a particle that goes through that little annulus happen to go exactly into that particular d omega? What is causing it to do that? Somebody tell me. Think.
I mean, all the particles within that d sigma have a fixed distance from the common axis, and so you'd expect them by the cylindrical symmetry to get deflected similarly.
Yeah, but what is causing them to go into that? Maybe this question is almost like too simple. It's like a trick question, but I'm asking you, what is causing them to go into that particular solid angle and not a different solid angle? I just want to emphasize that there's a connection between d sigma and d omega. They're connected, but what is connecting them? It's almost too simple of a question.
Is it just the potential?
Yes, exactly. It's the potential. Because see, if I had a different potential, then you see the d omega would be different. I just want to emphasize that. If the potential was stronger or weaker, the d omega would be different. So I just want you to understand that there's a connection between d sigma and d omega. They are connected by the potential. And it is that connection between d sigma and d omega that is the whole point of everything. That is the whole point of scattering, is how is the d sigma and the d omega connected? And that's it. And so that's the whole point. Because in the end, there's going to be this weird quantity, which is the ratio d sigma d omega. Because if these two things are connected, then I can think of the ratio, and the ratio between them has meaning. And that turns out to be the most important thing in scattering. It's that ratio. And this thing is called the differential cross section. Differential cross section. And it's just a bunch of equations. It's really easy to write them all down. But the reason why I'm trying to emphasize these connections is because I know that if you've never seen this before, it's really weird and kind of alien and strange. Why do I have to think about this little annulus area? Talk about the scattering is happening on the right. Why do I care about that little area on the left? Who cares? But it turns out that they're all very connected. And so because it's the particles that are going through that little bit of area that are then deflecting into different solid angles. For example, if I picked a different area, for example, what if I picked an area here where the area is smaller and I shoot my particles through a different annulus, a smaller one, and they go, and if this is a repulsive potential, where are they going to scatter? Is the theta going to be the same, smaller, or bigger? It's a question. 3 choices: same, smaller, bigger. Somebody answer. Talking about theta. Guess. Same, smaller, or bigger?
Bigger?
Yeah, exactly, because it's closer, it's repulsive. So exactly. So this guy is going to come here and it's going to go bang, right? He's going to scatter like that. And if I had him coming in on the other side, he would do the same thing, but down below. So he's got a bigger theta. So you see his theta is going to be bigger. Theta prime. On the other hand, if I send a guy out here, look at this guy. Now I'm sending him from very, very far away. What's his theta going to be? The same, bigger, or smaller?
Smaller.
Exactly, because he feels less of a potential, so he's going to deflect, but less, you see? So his angle is going to be smaller, theta double prime. So I just want you to understand there's this very intimate connection between the area and the angle. And the angle gives me that solid angle. And so I just want you to just get some sense that there's a very profound connection between this d sigma and the d omega, and that leads to this ratio, the differential cross section. And so let's just talk about spherical geometry for a second. We did spherical geometry before, but I know that some of you probably haven't even thought about solid angle for a long time, or maybe never. Maybe it's the first time you ever heard the word solid angle, which is sort of a bummer, but that's okay. You got to hear it sometime. And so let's talk about solid angle for just a moment, because in scattering we talk about solid angle all the time. So we're going to be using that word a lot. And so how do we think about it? And so let's first just think about angle. Everyone is used to this concept of angle. I draw a circle, and I can have a radius, and I can sort of carve out an area, theta, and then I have this arc length here. What do I call that? I'll call that S. And everybody knows that I can define theta is equal to, somebody tell me, angle. What's the definition of angle? Somebody tell me.
S over R.
Yeah. What are the units? What are the units?
Radians.
Yeah, but otherwise known as nothing. No units. It's a trick unit. Radians have no units. So it's a trick, right? There's no units. But we just call it radians because, we got to call it something, right? So you guys are all used to that. So angle has no units, but we still know that there's going to be 2 pi radians. in a circle. So, okay, so we won't belabor that fact. But now but what we have to do is we have to now generalize this concept of angle into 3 dimensions, because this angle that I just drew was for 2 dimensions. Now let's do it for 3 dimensions. And I'm assuming most of you have done this already, but this is sort of this is a review of solid angle. So let's generalize that into 3 dimensions. And so for 3 dimensions, what we got to do is we got to do this. We go to spherical coordinates. We have our r, we have our theta, and then we have our phi, right? We have our little friends. And then what we do is we draw the little thing here. What do you call it? Like the little window up there, right? And we have the, we have the little guy here. I did this all last time. I'm not going to do it all again. But this is like DL1, and this is like DL2. And we defined all this in the last lecture. So go back to that lecture to do all that. And you guys have all, we did this. You've all done it. And so we can define a little area. dA is equal to DL1 times DL2, right? And so then you know what this is. dA is equal to r squared sine theta d theta d phi. Okay, that's what it is if you work out the details, and we did work out the details last time. But then this distance is r, and so what we can do is we can look at this area. So this is dA, but what we can do is we can generalize it. We can say, well, in 2 dimensions, we can say in 2D, we have theta, we have d theta equals ds over r, right? That's what we did here. But now we can generalize this to, in 3D, we can define this new 3-dimensional angle, which for lack of a better word, we'll call solid angle, and we'll call this d omega. And so if in 2D it's ds over r, in 3D it's got to be dA over what? Somebody tell me. I'm defining a new type of angle in 3 dimensions.
R squared.
Yes. And what are the units? Why did it have to be r squared? It had to be r squared. Why?
Because you want it to not have any units.
Yes, because angle doesn't have units. That's exactly right. So that is the definition of solid angle. And so then we look from our little definition of dA, and so we can see that then the differential solid angle is going to be dA over r squared, which is going to be sine theta d theta d phi. And if I integrate d omega over all of theta and phi, what is it going to equal?
Get your 4 pi steradians.
Exactly, 4 pi. And there are no units. It has no units, but we always feel uncomfortable with that. So we just make up a little saying. We call them steradians because we're all stir crazy from COVID. There, steradians. And so this theta is equal to 0 to pi, and phi is equal to 0 to 2 pi. Okay, so that's our solid angle. That's your solid angle refresher. And so now let's, okay, so I'm sorry for doing all that, but I think it's useful because now I want to go back to this picture, because now I want you to sort of understand that, we have this connection between area and solid angle. And so I want you to visualize now the particles that are scattering into this solid angle. I will circle it here. See up there. Okay, so now what we can do is what we can do then is we see that if I define this ratio of the differential cross-section equals d sigma d omega, then what I can do is we can then, and this is, and by the way, this is for this is a function of theta, because look, this is the d sigma and this is the d omega for a particular value of theta. And so the connection d sigma d omega are connected. There's an angle theta, because if I have a different d sigma, I'm going to have a different d omega for a different theta. They're connected. So this ratio d sigma d omega is a function of theta. And so then what I can do is I can define, and this is just a definition, I can define something is equal to the integral of d sigma d omega. I can take this quantity, which is a function of theta, and I can integrate it over all solid angle. Meaning I can integrate it over theta and phi. And if I integrate that thing over all solid angle, what do I get? What do I get?
Just sigma.
What are the area? What's the units of sigma?
It's an area, right?
Yeah, it's an area, and it has a name. What's it called?
Cross section.
That's right, total cross section. That is the definition of the total cross section. And so it's kind of a funny thing, but you know, when you see it for the first time, it's not very intuitive. At least I certainly, it took me maybe 10 years before it started making sense. But this is the picture. So I have this, I'm shooting my particle through this little area, d sigma. The particle is coming through that little area. It's shooting off into some cross section, and here's the cross section into some solid angle. This is the solid angle, it's the eyeball thing. And so that's my d omega. And so you can see then that as I start shooting through all the different angles, like if I make this like a tree, you know, like the rings of a tree, and as I start shooting through all those little differential angles, all these little differential areas, I'm going to start hitting all of these different solid angles. You see what I'm saying? So there's going to be a mapping between every single little area and every little single solid angle. And so if I add up all the solid angle, there's a finite amount of solid angle. Solid angle goes from 0 to what? Tell me.
Or pi.
Exactly. There's a finite amount of solid angle. It goes from 0 to 4 pi. And so if I add up if I look at all the different solid angles that the particle can come out of, it's finite, 0 to 4 pi. And so then that means that if I then add up all the little rings of the tree, that means that the finite amount of solid angle has to then map, because I'm mapping solid angle back to area, it has to map to a finite area. And that finite area is the cross section, the total cross section. So that's what this integral is telling us. It's just adding it all up. And so when you think about it, this concept of cross section is very natural. It's like really it's like the best way to think about scattering, because that area then is then connected to the total amount of scattering. So I want you to think about that. But this mapping depends on the potential. And so what that means is that every potential is described by a cross section. So if I have a potential, I can then describe the scattering strength of that potential by the cross section. So that's a characteristic of the potential. Okay, so let's keep thinking about this. And so let's try to make this, let's try to make this like an experiment. And this is all very physical. This language is very physical because in an experiment, we measure this stuff. The reason this is also important is because we actually measure it. People measure it. And so like, look, this is what I can do. I can say, what I can do is, check this out. I can actually shoot particles through this d sigma. In an experiment, I could shoot I can shoot some luminosity of particles per area per time, and I can shoot them here through this d sigma, and then I can measure them. There's my sphere, and so then they're going to go out. See, I keep drawing this drawing into some d omega, and I can put a detector there. And that's a detector. And the detector counts particles. So I can make my detector cover that same solid angle d omega. And that's why when you go to CERN, you see these weird chambers, these spherical chambers with detectors all mounted on a sphere. Have you guys seen that? Like in pictures in magazines, they make, you know, they have like at CERN or these scattered high energy experiments, they like put detectors all in a circle around the interaction point because they want to see what particles are going into solid angle. And so it's a real thing. And so what I can do is I can count. The detector counts particles, and I can count those particles, and I can count them, and they're going to be dn. dn equals number of particles per time that go into my detector. And so if I know this relationship between d sigma and d omega, if I understand that relationship, then what I can do then is then I can write I can write a relationship between these things. I can say what I can do is I can say that the number of particles per time that go into my detector, dn, is equal to what? I have luminosity, I have d sigma. What is the relationship between luminosity, d sigma, and dn, which is the number of particles per time that go into my detector? Somebody tell me. I want you to relate those things in your mind.
It's like L times area.
That's exactly right. It's really simple. It's really quite simple because every particle that goes through that d sigma goes into the d omega. And every particle that goes into d omega, I count in my detector, dn. So there's this very simple, beautiful relationship here. And the reason why I emphasize is because this is real, it's experimental. Like you measure it, you measure it in a laboratory. It's not just academic, you actually measure it. And so I can define this. So this is where sort of the rubber meets the road because, we're talking about all this abstract quantum mechanics stuff, but now I'm talking about experiments. You can measure it. And so what we can do then is we can go one step further because this is a very simple relationship, which I think is sort of geometrically obvious. But then you can just take the very next thing because you can say, well, if that is true, then I should be able to write d sigma is equal to 1 over the luminosity times dn, where that's the number of particles that go into my detector. And so, but if that is true, then what I can do is check this out. I can divide both sides by d omega, the actual solid angle covered by the detector, These are not just random variables, but they're all related. D omega, I'm dividing both sides. And so look what I've just done. Just what I've done is I'm showing you that this quantity, d sigma, d omega, the ratio between that little differential area and the solid angle that the particles go through is equal to 1 over the luminosity times the number of particles per time that I measure divided by the solid angle subtended by the detector. So this is the number of particles that I measure, number of particles per time that I measure, and this is the solid angle of the detector. And so what I want you to, and luminosity is just the number of incident particles, the number per time of incident particles. And so what I want you to see is that these three quantities, the number of the luminosity, the number of particles that I measure, number of particles per time that I measure, if I just put them in this very simple ratio, then they equal the differential cross-section. And so from this, you can see that the differential cross-section is thus the most natural experimental quantity to think of. Because when you measure a scattering experiment, there's three things you have. You have the number of particles per time that come in, the luminosity. You have a detector, and you're counting the particles per time, and you know that's the area, the solid angle of your detector. Those are like the three main things. And so you put them into a ratio, and that ratio is exactly equal to the differential cross-section. And so I want you, the reason I'm going on and on about this is that I want you to see that the differential cross-section is the most natural quantity to describe scattering. There is no other quantity that makes sense. It's the most natural, fundamental way of thinking about scattering, because it's this very simple ratio of all the things you measure. So, okay, so I want you to feel like it's firmly grounded in logic and just like simple stuff that you measure in the laboratory. Okay.
I have a question about this.
Yeah.
So wouldn't you need to build a detector that already has the same area as corresponding to the d sigma that you're sending out your particles at? Otherwise, you would get like high flux in some areas of your detector and low count.
Yeah, but look what I can do. Check it out. I mean, I could just take a piece of metal. I could just take a piece of metal and I could just cut a little, you know, if I wanted to, I could just cut a slot out of it, right? Like that. And that's my, and then I could just have like a slot here, and then I could actually construct my D sigma. And then if I have a room, I could just put detectors everywhere in the room. And then I could shoot my particles and I could just see which detectors light up. I mean, I can completely define. It's like I define the D sigma and I measure the D omega. Is that addressing your question, or maybe I'm going off and on?
Yeah, I see. That makes sense. I for some reason I was thinking that you were saying that one detector was counting some dn, and that detector had a solid angle d omega. But I see if you have them all around the room.
Yeah, it does. But what you just said is correct, and that d sigma corresponds to some little area, dA. D sigma, you know, for when the beam is coming at. But the relationship you don't know, you know. So the way to measure it is like I could just define a little area, only let particles go through that little area, and then see which detector lights up. And then I can physically measure the relationship between D sigma and D omega. I want you to see that. I mean, it's something that you can really measure.
Yeah, that makes sense. Thank you.
Okay. Right, because the thing is, we're about to go off into, you know, quantum mechanics, you know, abstract land. But before going into doing all the abstract quantum mechanics, I want you to see that this is like stuff that you measure in the laboratory. It's not just academic. You know, it's very physical. Okay, so now that I've gone off on that tangent, we haven't even done quantum mechanics yet. We've only been doing classical stuff. Now let's do quantum mechanics. How do we do quantum mechanics?
Quick question about the d omega. So when you increase like your impact parameter by a little bit, or you have like this d sigma, you get like this little increase in solid angle in the northern hemisphere, and you get this little increase in the southern hemisphere. This d like omega, the solid angle, does it refer to like both of those at once, or are like, because wouldn't you need a detector like up there and then like symmetrically below the axis, or does it refer to both at the same time?
It's however you want to, because look, it's the d sigma and the d omega are related. If I, for example, if I look at this picture, I mean, for example, if I do this, and if I only did the upper half, then it would only go into the upper half, you know? See what I'm saying? It's like, there's always going to be a relationship. However I define d sigma, there's always going to be a relationship between d sigma and d omega. On the other hand, if I only did this quarter, then it would only be, you know, I don't know, 1/4. You know what I'm saying? There's a relationship.
Yeah.
Okay, so now let's try to understand quantum mechanics. And so, okay, so this is the thing. So this is how I want to do it. I mean, there's different ways to approach this. This is my favorite way. So here's classical, and then we're going to do quantum mechanics on the right. So classically, let's look at classical scattering, and then there's quantum mechanical scattering. And so let's do it like this. So classical scattering is this. We just did it. We have some we have some luminosity, and the particles scatter. I have a V of R. I have a luminosity that's incident, right? The incident luminosity of the particles coming in from the left, and they scatter off into some solid angle. And the solid angle is the eyeball thing, the eyeball construction. It's my solid angle, which corresponds, of course, to this, you know, this annulus d sigma. And then, okay, so I have the L, and then here, and they're going into some detector, which is like this whole, you know, this whole solid angle detector that has to cover the solid angle. And so the number of particles going into that solid angle, d sigma, or I'm sorry, d omega, which is the solid angle of the detector 2, is dn. That's the number of particles per time that I measure. Whereas the luminosity is equal to the number of particles per time per area that I send in, per area. And so, per area. Okay, so that's classical scattering, all right? I think that defines everything. And then from this, we see then that we have, we just figured out that we can define the differential cross-section, d sigma d omega, is equal to 1 over the luminosity times dn d omega. This is the most important quantity, the differential cross-section, because that's telling me the ratio of the number of particles that I measure divided by the solid angle of the detector divided by the number of particles per time per area that I sent in. So this is the most important quantity. 3 stars. That's the thing we care about. And we measure it. You know, you measure d sigma d omega because we measure that in the laboratory. Because we can measure L, we can measure dn, and we measure d omega. I just want to emphasize this is experimental. You measure these things. It's not just academic. Okay, so that's classical scattering. Now let's do quantum mechanical scattering. How do we think about this in terms of quantum mechanics? So in quantum mechanics, we're going to have the same thing. We're going to have the same construction. We have a potential. And we're going to send something in. But here's the thing. Okay, now this is the thing. Check it out. We send in a wave because a particle with a well-defined energy is a plane wave. And you learned that last semester. So we're going to send in a wave. And that wave is going to be my incident wave function, the incident. And that incident wave function I can write with a little equation. What is the equation? Somebody tell me.
Is it e to the I k r?
Yeah, exactly. That's exactly right. It's a plane wave. And so it's going to be e to the I k incident. The direction it's moving is the k. It's a vector. And in 3 dimensions, I got to do a dot product, right? That's a plane wave. That's right. And then to normalize it, let's put everything into a big, the normalization can be is a pain in the ass, but let's just normalize it. I put everything into a big box. 1 over L to the 3/2, where L is the size of the box. And let's just say the box is the universe. Or, I don't know, let's just say it's the universe is the room I'm in, 20 feet by 20 feet, whatever. It's a big box. So I'm in a big box. I've normalized my wave function, my universe. And then that particle scatters. And when it scatters, the particle is going to interact with that potential. And so in our mind, what we think of is that the particle has a certain momentum, but now when it interacts, it's going to have a transition to a new state. And the new state is going to take me into a new direction, a new momentum. And so now my particle is going to suddenly start going in this new direction. And that's going to be the final direction. So I'll call that direction K final. Because this direction is the initial, the incident direction, and that's my final direction. And so what is my, well, let's draw the construct, before I write the thing, let's draw this. So now let's draw the sphere, because I want it in your mind that the pictures are connected. So there's a sphere. I can draw a sphere around this spherically symmetric potential. And then I can say that this final direction defines a solid angle. And so I can just do the same thing. I can define this solid angle, and there's an angle here, theta. And so now this final, I scatter into this new state, and how do I define the new state? What's the equation for the new state?
Just e to the I k f dot r.
Exactly. It's a plane wave going in a new direction. Exactly. And let's normalize it to 1 over L to the 3/2. So this is the picture that you should have in your mind. I start in some incident state, and I scatter into some final state. But now, but then how do I connect? But here I had the incident luminosity. So what is the quantum mechanical analog of the luminosity? Because the luminosity is here defined as number of particles per time per area. What's the quantum mechanical equivalent of this?
Is it the probability flux?
Yeah, exactly. It's the J incident. It's actually a vector quantity, but I can take the magnitude. And so instead of the number of particles per time per area, what are the units of it in 3 dimensions? Somebody tell me.
Probability per time per area.
Exactly. Because it's probability flux. This guy is particle flux. And so this guy then is probability flux. That's exactly right. And so now let's take it a little step further. So now on the classical side, I have d sigma d omega, the relationship between that little piece of area that the particles go through and the final solid angle, is equal to 1 over the luminosity times dn d omega. So now let's do the quantum mechanical one. I have d sigma d omega. Now what's the quantum mechanical analog of the luminosity? What do I use? Instead of luminosity, what do I have on the bottom?
Probability flux.
Exactly. Incident probability flux. Now I have this ratio. Now on the bottom I have the same thing, because here I have this d omega, because I still think of the particles as coming out of some solid angle, even though it's quantum mechanical waves and all that. I can still define the direction, you know, because the direction is defined by the angle theta, right? And that angle theta is scattering into some solid angle. I guess I could think of it as, I mean, we also have the angle phi. You know, the solid angle is defined by theta and phi. So on the bottom here, I still have d omega. But what goes on top? Classically, it was the number of particles per time per area going into my detector. Now, quantum mechanically, we can also think in our minds that up here, I have a detector. I'm still detecting stuff. But what is it that I'm detecting in quantum mechanics? What do we detect? What do we measure? What's the stuff that we measure in quantum mechanics? What is the detector detecting in quantum mechanics? What goes on top? Tell me.
Is it the probability or probability density?
That's right. Here I have number of particles per time. Jeez, this thing keeps freaking out. That's particles per time that I measure, number of particles per time. What goes on top of this ratio? I replace the number of particles with what? What per time? You can see it right here. Look at the luminosity. What are the units of the luminosity, and what are the units of my J incident? The number of particles got replaced by what?
Probability.
That's right. And so here in this ratio, it's the number of particles per time. So what goes on top of this ratio? I want it to be precise. Get the units right.
Probability, right?
This is particles per time. What goes on the right-hand side? Tell me.
Probability per time.
Exactly. What do we call probability per time? It has a name. We defined it already in our discussion of Fermi's golden rule. What is probability per time?
The rate.
Rate. Exactly. Rate. That's why this concept of rate is so important in quantum mechanics. Probability per time is rate. And so I'll call it dr. It's the rate of particles going into the detector. That's why I don't call it r, the total rate, because the particles could be going in all directions, but we're only talking about the particles that go into one particular direction or one particular solid angle. Because here there's a relationship between dn, and these are not independent variables. They're connected. We're talking about the number of, on the classical side, we're talking about the number of particles that are going per time going into that solid angle. And here in the quantum mechanical part, it's the same thing. We're talking about the probability, dr, that is flowing into that solid angle. Because probability is like water. That's why I keep emphasizing this idea that probability is like fluid. It's stuff, it flows. Think of the probability as actual fluid, and that will help you. I spray the probability, I'm spraying the probability at the potential, the probability splashes up against the potential and sprays outward, and some of the probability fluid flows into my detector. And as I keep spraying the probability, the probability that flows into my detector accumulates in my detector. Probability per time, it's accumulating, it's going in there. there's a rate at which it flows into my detector, and my detector is capturing it. And that's how we connect physical reality with all of these weird quantum mechanical concepts. You see, this is the connection. So I want you to think of it in like, have that connection. And so that's it. And so now we have that's the quantum mechanical theory of scattering. Quantum mechanical scattering, we did it. In quantum mechanical scattering, we then have this quantity, the differential cross section, d sigma d omega, is equal to 1 over J incident times dr d omega. And this is, and dr is the probability per time for the probability to flow into the detector. So this then is how, if someone now were to say to you, calculate the, if someone gives you, so if I give you this, if I give you this potential V of R, I can then say to you, what is the differential cross section of this potential? And so then what you have to do is you would then have to calculate d sigma d omega is this quantity. And then I could say to you, I could say, well, I could say to you, well, what is the number of parts? I could say, well, suppose I shot a bunch of particles with some luminosity at this potential, and I could say how many particles go into a certain solid angle, and then you would say, well, I could say, you know, how many particles do I expect to go into my detector? Well, you know that the number of particles into the detector is equal to the luminosity, and we already did this, times d sigma d omega times d omega, and this is the number of particles that go into my detector. And so I could say to you, if I have some potential and I shoot a number of particles at it, how many am I going to detect? And then what you could do is, this is the size of my detector, the solid angle. This is the number of particles I start with that is known. But then how do I get this? Well, this thing then you get using quantum mechanics. And what you have to do then is you have to calculate the quantum mechanical quantity, which is d sigma d omega is equal to 1 over J incident times dr d omega. And so if you calculate this quantum mechanical quantity, then you could predict how many particles go into the detector, because that's literally the number of particles that go into the detector. So what I'm trying to do is to take these abstract quantum mechanical concepts and connect them to physical reality. So, you know, so if you can calculate the differential cross section, then you can predict how many particles go into your detector. And that's very, very important, because if you're a high energy physicist trying to build a detector at CERN, you need to think about how many particles go into your detector. And you need to think about how quickly they go into it, because that will determine the electronics, and that will determine the noise level and the detection efficiency, and whether you have like really fast electronics or slow electronics. It determines everything. And that determines, and the most important thing that it determines is how much that detector is going to cost. Because in the end, it all comes down to money. Someone's got to give you enough money to build the goddamn detector. And you got to be able to go to that person who has the money. You got to say, come on, man, I need $20 million. Because if you don't give me $20 million, I won't be able to detect the goddamn particles, because I did my little calculation and I get this many per time. And that means that I need a detector that can count that rapidly. And it's going to cost me $20 million, you know? And so you got to convince them. So it all comes down to money. All right. So, okay. So then the question becomes, how do we calculate? So if you're a high energy physicist and you want to ask the government for money, you gotta prove to them, you know, you gotta make a convincing argument that they should give you a bunch of money to detect those particles. And so what you gotta do is you gotta calculate this quantity, this differential cross-section, because that's where all the physics is. So how do we calculate this thing? So if I say to you, you know, here's a potential, what is the differential cross-section? Then you have to calculate this quantity. And how do we do it? Well, okay, so that's the question. Well, of course, we're going to use quantum mechanics. And so here's the picture. Here's the potential. I'm sending in my particle some incident wave, e to the I ki dot r. It's normalized. Let's normalize it. That's my incident wave. I'm going to have some scattered wave. My final 1 over L, so 3 halves e to the I k final dot r, and this is my detector, covering a solid angle d sigma. And how do I? And now I got to calculate all these quantities. So I need to find. There's 2 things I need. I need to find J incident, and I need to find this other weird quantity, dr d omega. Okay? And so this is where all the quantum mechanics comes in. We've got these quantum mechanics to find these quantities. And once I find them, then I get the differential cross-section. And the differential cross-section is the most important thing, because that's going to tell me how expensive my detector is gonna cost. Okay, so let's find these things. So first, there's 2 things to find. One is easy, one is hard. Let's find the easy thing first. J incident is really easy. How do we find J incident? Somebody tell me.
We just plug in the incident wave function into the equation.
That's exactly right. It's h bar over 2mi. We just used the equation that you guys derived last semester. Psi star del psi minus psi del psi star. You plug it in, and I'm not going to do the math, but it's really trivial. It's really simple. You just take that guy and you just plug it into there, and then then out pops the answer. And I'll just tell you what the answer is. Because it's really simple. Just a few lines of algebra, and this is the answer. H bar k incident over ml cubed. Okay, that's the answer. And it's actually a very intuitive answer, because check it out. This is equal to, if you have a flux is always equal to a density times a velocity. Density, every flux is equal to density times velocity. And so this is a probability flux. And so the probability density is 1. That's how much probability you have per what? The probability of finding my particle is 1 over a certain volume. And what's the volume?
L cubed.
Yeah, the size of the universe. So that's probability, that's the density, that makes sense. And then the velocity is just h bar k over m. Because h bar k is what?
Momentum.
Right, momentum divided by mass is velocity. So I just want you to see that this is a very intuitive result. Okay, so now let's do the second thing. Now we got to do the next part, which is really hard. The next part is really hard. Okay, so how do we do the next part? Okay, we got to figure out the next part, which is we're shooting the particle in, it's interacting, and it's coming out into some angle. And we want to know dr divided by d omega. So it's coming into some solid angle. So, all right, so this is the way to think about it. I have the particle coming in like this with some incident momentum, and it hits this potential, that's the V of r. Now the particle can go in any direction. So these are the final states. It's like a porcupine. That's how I like to think about it. It's a porcupine because there's all this, the final states are a porcupine because it can go into all these different areas, all these different directions, like the spines on a porcupine. So it's a porcupine. So there's many, 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 many different directions it can go in. And that's I just want you to see that that's a continuum of states. There's a continuum of states it can go into. But we're only concerned about one solid angle. So of all this millions of states, we just care about this cone of d omega. And so these are all the possible final states. So I'll call these final states rho at the energy, whatever is the energy, is equal to the total number of states final total states per energy. And so what we can do is we only care about a small number of them, d rho. And so that's going to be equal to the total number of states times a ratio. And can you tell me what that ratio is?
d omega over 4 pi.
That's right. So those are exactly, and that's because the total amount of solid angle is 4 pi, but we only are caring about a little piece of it, the d omega, which is the solid angle of our detector. And so that's the final states that we care about. So this is the initial state. We're starting in a well-defined initial state, but what we're ending up in this dense continuum of states in d omega. The continuum of states, the continuum of final states is this. D rho is equal to rho, the total density of states, times d omega over 4 pi. All right, that's the picture that you have to see. Like you're starting in an initial state, and then you're ending up in a dense set of final states. You're scattering into this d omega, which is a dense set of final states. And so now I want to ask you a question. What is the rate to scatter into that dense set of final states? The rate of scattering. I won't say rate of scattering, I'll use a different word. I'll say the rate of transitions. Because this is a transition problem. I'll call it dr. What is it equal? We're starting in a well-defined single state, and we're ending up in a dense set of final states. And I'm asking you, what is the rate of transitions? We have solved this problem before. I know that some of you know the answer. So what is it? How do I calculate this using quantum mechanics? In case that doesn't ring a bell, let's look at it like this. Let's check this out. Here's an atom. I'm sitting in this initial state. I hit it with some light. It gets excited to this dense set of final states. Doesn't that look familiar? We start at a well-defined initial state. Like now, it's the momentum. We end up in a dense set, a continuum of final states. We did this problem.
Would it be the probability current integrated with the density of states or something?
Well, yes, we can connect it, and we will in the future in this class connect it to that quantity. but now I want something else. I'm looking for something else. Like this problem that we solved in class, it led to an answer. What was that answer? What was the rate of transitions?
It was Fermi's golden rule.
Yes. And what was the little formula that we derived? It was pi over 2h bar times the matrix element squared times the density of states. Yeah, you guys remember that? Rate is equal to pi over 2h bar, the matrix element squared times the density of states. Yeah, does that sort of sound familiar? You guys remember that, right? And so that's Fermi's golden rule. And so that means that now we can use that here because we have the same thing. We have the constant in front, and then we have the matrix element squared, and then we have the density of states. Density of states. And so, okay, so let's start with the density of states. What's the density of states? What goes here? There's three things in Fermi's golden rule. What's the density of states used for our problem?
E rho of E.
That's right. That's right. What's the matrix element? What's the thing that's what's the H prime? What's the perturbation? What's the energy? What's the thing?
It's the electric dipole operator.
That's a good guess because that's what we did for the electric field. But now I'm not giving you an electric field. Now all I'm giving you is this potential V of R. So what is this matrix element? Let's write it here. It's a matrix element. This is a matrix element. It's got three things. It's got an initial state, it's got a final state, and it's got the perturbation.
So would it be like the incoming wave, then V of R, then the outgoing, the transition wave?
That's exactly right. The initial state is going to be the incoming wave, e to the I, k initial dot r. The final state is going to be the outgoing wave, which was e to the I, k final dot r. And the perturbation, the thing that's making it transition, that's the energy. It's the Hamiltonian. And what goes in there?
V of R.
Yes, exactly. And so this, we'll call it like this. We'll call it VFI because it's the matrix element that connects the initial state to the final state. Initial, final. It's a matrix element. And V because it's the potential V, the potential, you know, the V of R of the interaction. And so that's right. And so that goes here, VFI. And then what goes here in this little middle part? The constant. Well, the constant should be pi over 2h bar, right? But it turns out that there's an annoying little nuance. It turns out it's 2 pi over h bar. There's a factor of 4. Factor of 4 because V of R equals constant. If you go through the math that we did, and I'm not going to go through it all right now, but in this Fermi's golden rule, in the one that we derived before, we had this. We had a sine omega t. We had a sine omega t factor, and in this one we have a constant. There is no sine of omega t. There's no sine of omega t. And because there's no sine of omega t, then it turns out that there's a factor of 4 that gets carried through the math. And I'm not going to do that. You know, you guys can try to do it on your own or look it up. But but there is a factor of 4. That's why this constant is a little different. I realize that for some of you, that's gonna be really annoying. I remember when I was an undergraduate, that factor of 4 just confused me. I was like, what the hell, where did that come from? But if you follow the math, you can see it, you know, it comes right out. So there's this little factor of 4. So the constant is ever so slightly different, but that's the answer. And so now we have it. So now what we have then is we can find, we have this relationship. So we have dr is equal to 2 pi over h bar vfi squared, and then we have this d rho of E. So the question then becomes, what is d rho? That's the hard part, because this is defined. You know, the matrix element is an integral, because we see that vfi is well defined. It's just going to be this integral of, you know, 1 over L to the 3/2 e to the minus I kf dot r v of r times 1 over L to the 3/2 e to the I k initial dot r d cubed r. Okay, so the matrix element is well defined, but the only thing that we don't know is this stupid, weird little density of states thing. And so we know that d rho is equal to the total density of states times d omega over 4 pi. So then the question becomes, what is the total density of states? Okay, and so we're sort of running out of time, so I don't have time to do the whole derivation, but I'll just sort of mention it. Like, to do the derivation, you would have the total, you know that the total density of states times a little bit of energy is equal to the density of states in K space times a volume in K. And so then you have to relate them, because then we see then that the rho of E, the density of states, is equal to the density of states in K space times d cubed K over dE. And so we have to calculate this quantity, and that gives us the density of states. And so there is some math. So unfortunately, I don't have all the math, all the time to do it. But when you can calculate it, and it gives you, there's a very simple answer. You get m L cubed K over 2 pi h bar squared, 2 pi squared h bar squared. And so when you plug that all in, you see that you have, you can have, well, now we can plug it all in. We see dr is equal to pi over, it's going to be 2 pi over h bar times vf squared times this ml cubed k over 2 pi squared h bar squared times d omega over 4 pi. And then I can pull this underneath, and I get dr d omega. I just want to write this answer down, and then we'll be done. It'll be 2 pi over h bar v fi squared times ml cubed k over 2 pi squared h bar squared times 4 pi. So you see, we can actually calculate this quantity, and then we plug that in, and it gives us the d sigma d omega, right? Because d sigma d omega was 1 over j times dr d omega. Okay, so I just sort of, I'll go through this again next time, but I just wanted to sort of get that answer. I just want you to see that this is the answer. We have calculated, just plug it all in, and that is how then you calculate, that's how you calculate the d sigma d omega using quantum mechanics. And I realize I kind of rushed it here at the end, and I'll go over that again next time. But I just wanted to, get to the final answer before finishing the lecture. Okay, bye-bye.